Can you hear me now?
Yes, go ahead.
Yes. So for this paper, the origins and evolution of life is one of the most important and exciting scientific questions in science. So for this paper, it tried to explore the deep time evolution of the biosphere. So because we could use the 3D dimension, that is deep time, deep earth, and deep life. And the first author is Henrik, and from Linnaeus University, and his research interest focused on the geochemical and geobiological aspects of the deep life. And also the second author is Peter from the University of Arizona. He also a geochemist and geobiologist. So I'm going to give highlight of this paper. First, the paper just provide a new method about the thermochronological perspective on the habitability of Earth's Precambrian cratons through time. And second, is that this paper just interprets the little exploited geological record of the deep biosphere of Earth's different cratons. And it also forecasts the candidate areas for the oldest records of subsurface microorganisms. Over the last decades, the most important advances that we have achieved about the life evolution is that we have known more about the deep life. For example, the microorganism could host in marine sediments, and also the hot, hydrothermal vents and all the oceanic fractures could also host the microorganisms and the microbial life. Apart from that, scientists also find that the ancient life in igneous rocks and metamorphic rocks. And recently, scientists find that this deep subsea floor microlife could survive in 120 degree and 20 degree. And also for the LDP program, scientists from the Chongqing University they find the heterotrophic organism in the low oceanic crust. It means that in low oceanic crust, the microbial life could transform the limited nutrients into the energy for the microbial surviving. The scientists found that the concentration of the deep life of cells just decrease with stage, and we can see that. Actually, the Earth's deep biosphere hosts the majority of the microbial life. So current estimates show that 90% of the bacteria and archaea survive in deep biosphere. And if we turn the clock back into the 700 million years ago, in the surface, the plants or vegetation got to be prosperous and in the Carboniferous. And before that, the deep biosphere just hosts the majority of Earth's biomass. But even for that, the Earth's deep biosphere is one of the most least explored and understood environments. For example, when life colonized the deep biosphere and of the fractured crust, how the microbial life may evolve in deep earth and persist through time. We know a little about that. So for this paper, I'm going to talk about the method. So in this paper, they also use the thermochronologic approach, that is the argon dating and the fission trick and uranium and sodium helium techniques. And using this method, it could provide in the temperature and time constraints of the different cratons. So in this paper, the author points out that the temperature is the most important factors that affect the habitability of the deep biosphere. For example, the 70 to 120 degrees is the habitable for microbial life. So if you want to access the histories of habitability of different cratons, it means that you have to get the thermochronological record of them. So firstly, they also just get the thermochronological record of a Canadian shelf. So why did it also just choose this field? Because it has the oldest deep content of fluids. It means that life could be more likely to be surviving in these with these fluids, and also the Canadian shelf has the rich thermochronological data set. And second, also just focus on the Fennoscandian shield, and coupled with the thermochronology record and biosignatures of this craton. Last but not least, also just give global perspectives of different cratons with the thermochronology data. So for the Canadian shield, this is the location map of these samples, and this is the thermal history of this Canadian shelf. Let's see the Superior 70, and for this location, we can see that the green color means the habitable for a deep biosphere life. It means that the temperature is lower than 100 degree, and for the red color, it means uninhabitable for deep biosphere, and because the temperature is too high and more than 120 degree. We can see that for most part of this, for this Canadian shelf, the habitability of this area is not earlier than 500 million years ago, and because in this area it lacks, the biosignatures evidence, so they also cannot compare the biosignatures with the thermal history of this area. So next, they also just focused on another craton, that is the Fennoscandian shield, and most of the samples from this southern of this craton, that is Sweden, that is here, and this that is the same thermal history just like the Canadian shelf. And because in this area, they also can get the biosignature and geochronology information of the bands. So they also just compared the thermal history of this area with the biosignatures, because the thermal history just the predictions, and we can use these biosignatures to validate this prediction. We can see for the 3A, we can see that for the thermal history just predict that in this time, because the temperature is too high and to be habitable for life, for surviving, and for the biosignature, there's no biosignatures here, so that is consistent with this prediction. Interestingly, that the thermal history just predicts in the 3B, it should be suitable or habitable for microbial life in the deep earth, but there's no biosignatures here. And one explanation for that is that there's no or the biosignatures has not been discovered yet, so it can be tested in future studies. For these 3 periods, this thermal history just predict that they are suitable or habitable for microbial life in deep earth, and also they also point out that there's a lot of biosignatures in these 3 periods. For example, that is the fractionation of the carbon and sulfate isotopes, and also the mesentropy, that is the activity of the biology in this deep surface. So that is consistent with the prediction of the thermal history. So last but not least, it also just give a global look of different cratons. And because for most of the cratons like the detailed geochronological and biosignature data, they also just use the limited, surface rocks and geologic cores to draw the habitability of these different cratons. And we can see for most of the cratons worldwide, few cratons has the continuous habitability of the deep biosphere older than 1 billion years ago. But there are 3 exceptions, and for Finland, Superior, and Greenland. These 3 locations may host the most longest or continuous habitable environment for the deep life. So for this paper, it just forecast or predict the candidate areas for the oldest records of the deep life or the subsurface microbial life. And it can be tested in a few studies. The most important for this study, I think, is that it could guide the few studies for finding the deep biosphere life. So that's the end for today's for my presentation. So we can discuss more about this paper. So much for that.
Okay. Thank you, Chengda, for leading the paper. Let us going through that. Okay. So actually, I have a quick question for you. Now, from your perspective, if you could get access to all the sedimentary geochemistry data, if you know not only in bulk rock, but also for every mineral composition that we could get in the Earth history. So how do you think that you could further extend their idea?
Sedimentary rocks, maybe some trace or magic elements could reflect the biosignatures of the of life, of the activity of life, and maybe.
For example, here they just show the stable isotopes like carbon isotopes. So what are type of other major trace elements you think that is related to life?
No, so actually I don't know which elements or trace or magic elements could reflect or reflect by the activity of microbial life. And I think the isotopes could be more sensitive to this to the activity of microbial life. But for the trace of magic elements, actually I don't know it will, if it could be reflect the activity of a microbial life. Maybe because I do not see the papers just reported, it could be reflected.
And then the other thing, the relevant things that, do you think that for all the igneous and mainly metamorphic minerals and rocks composition that we get, do you think that there are other low temperature equilibrium in terms of the major and trace element concentrations that we can also infer the temperature evolution in different cratons or ocean floor too?
If you want to use the, I think the igneous or metamorphic rocks or sedimentary rocks to constrain the temperature evolution of these cratons or different areas, I think actually, because I do not see any paper just to that, I do not see any correlation between these two things. Maybe you can see details of these problems or these questions in. Yes,
yeah. Yeah, because in the end that we are going to get all the igneous, metamorphic, and sedimentary mineral as well as the rock, major and trace elements. And I think one interesting thing actually to this paper too is that could the temperature be reflected in other ways? And I think that's our pushing for lower limit of the a much lower temperature than most of the igneous process. For example, for granite, even this is much lower temperature than granite.
Okay, I can
Uh,
understand.
yeah, it's lower than that. So we don't. I mean, they provide one grade. I mean, the argon, this uranium, thorium, helium dating. Like I said, a fission track. So that's good. I mean, for major trace elements as well as for other systems that could we also infer, even infer to push for this lower end might be interesting. And also I would like to point out that 120 degrees might not be the limit of life because that's the conclusion that either people get it from deep drilling or from the hydrothermal vents microbial life that is still at the surface. That's not the real deep earth biosphere life in the lithosphere. I mean, really in a deep crust. That's not exactly the case. Like, for example, you show here the sediment depth, like say it's how many meters? It's like say 1,200 meters, I suppose.
You see this, if you
4 kilometers, for example, this one is 4 kilometers. Actually, this is still not deep enough. It could be extended even further than that. Which so far there is a lack of constraints, but we might know in the future. My bet is that life limit could be further expanded from 120 degrees, much higher. I don't know how high. I don't think it's like 400, 300, but might be much higher. But still pretty low. For example, let's just take a face value of 200 degrees. Is still much lower than, for example, the temperature that granite begins to, rhyolite begins to crystallize. But still, I'm thinking about whether the other ways that we could constrain temperature to approach this problem, which is one most important question in science. I mean, not only in geoscience, but in science, is what's the limit of life, as well as what's the evolution of the bio life. Go ahead, Chunda.
Yes, I have to respond to your questions. Firstly, yes, maybe the temperature limit for life surviving it could be higher than the 110 degrees. And so actually for recent decades, for recent years, so scientists maybe found that the microbial life or the concentration of microbial life just decrease with depth, and as these figures show that maybe in the deeper it could be exist any other life. For example, maybe just as these figures show that in the deeper for the LDP program defined the heterotrophic organism. That means that you just get the energy from these rocks. Maybe it could help this microbial life to survive. And also, so actually, if you want to make the prosperous of life, as actually the low temperature, it will be more likely for life to survive or prosperous, I think. And for other thing that use the trans or major elements to constrain the temperature evolution of different quanums of the environments, I think maybe for example for the major elements, that's the magnesium. Actually, scientists often use these major elements to constrain the temperature evolution of these of the crust or the mantle. I think other major trace elements may also be reflect the temperature evolution of the rocks or the crust. Maybe not explored yet. So yeah, we can try it if we can try it in but it has to be discussed, or a lot of details have to be synced if you want to do that.
Okay, I think Lei has a question. I think Lei means the cell density, or do you mean? I didn't get it. Actually, I also have a question here, Chantal. So for the cell density here, do they mean the cell density in 1 milliliter of fluid, or do they mean?
For this paper, actually I didn't see details of this paper. I just actually this paper just published by biologist, and they just have you know, count. I think they count the I think
Yeah.
maybe
I think actually I could guess there is a instrument called flow cytometry, which you could count how many cells in the fluid. So for example, like say 1 million cells, basically could count every one. So I think this is like say you put 1 drop of water, then that's how much cell that you're going to get. But I think my question is that, okay, in the deep fluid, actually, okay, actually I didn't see they see it's interesting, right? So they see a trend of decrease of cell density until 2000 meters, but you go further, then you don't know. It might still be high. So they have this crystalline rocks. I suppose that's come from deep drilling projects.
Yeah.
Okay. I think that's this question.
Yeah.
Hi, Chantal. I have 2 questions. So, the first one is the oxygen necessary for this bacteria in the deep earth or in the deep biosphere?
Yes, oxygen is actually its most important limited factors that affect the evolution of or the surviving of the life in surface. But actually for deep life, and microbial life could get the energy from the rocks by the chemical reaction of just get the energy from this chemical reaction. So they do not the oxygen in deep surface.
Okay, I got it. Yes, and the second one is about the fluid inclusion, the life signatures. They use the carbon isotope, right?
Yeah, actually the author just stated the data was not reported by this author, we just referred to the reference work. You did not do by this author, just see the other researchers work.
Okay. So I'm just curious about is there many fluid inclusion have this very negative carbon isotope signature compositions? I'm not sure.
Actually, if you see if you read papers about the or the fractionation of let's say actually the activity of the microbial life is an important factor that affect the fractionation of isotopes. And for example, for the carbon and sulfur isotope, the activity of a microbial life could fractionate the isotope to very low and high value. I could say that the minus 125 per million, and that's very high than in the in the natural environments. And actually, I think in the paper, that also stated that, and also just point that only the activity of the microbial life could explain such a huge range of these fractionation of the isotopes. And actually, it also just leads to the bacterial sulfide reduction, and this reaction just helped by the bacteria, and this reaction could fractionate, the sulfide isotopes.
Yeah. Okay, I got it. But is there many cases like this, or just some few rare cases like that?
I think I think that there's many examples in this area.
Okay, got it.
Actually, this is an interesting one because I remember a couple of years ago, there was a publication published maybe in Nature Geoscience where people find a graphite in Jekyll zircons and show positive numbers. I don't know how positive, slightly positive, I think. And then people claim that signature of not life. Well, of course, that's not too convincing. But I think people are still looking for it.
That is too old. The rock.
Yeah, it's extremely loud, but we don't know. And the
Yeah.
evidence is not that strong, but people made a very brave or tentative claim saying that it's life signature. That is not conclusive for sure, but it raises a very interesting point.
Yes.
Yeah.
It's a big news for science, but it has to be tested in future studies.
I would like to make a further comment. I also ask you, Chantao, for you to explain, is that for following Ben's question, relevant to Ben's question, not following, I don't think oxygen is important for this deep bio life because they don't see the sun. So unlike majority of life in the Earth's surface, we see the sun, or in the ocean, or in any water is mostly 200 meters in the shallow part where it is to get sunlight going through. Then for the rest of it, this is all basically light free. So I don't think the oxygen is needed for the extreme conditions. However, it does need metabolism. That is, for people like you and me, we also need to drink and eat, and also get rid of things from our body. So that is metabolism, and for microbes too. And unlike those other microbes that needs oxygen or light at the surface, where that's how we obtain energy. For the deep life, it doesn't need that light or oxygen, but they do need energy for metabolism. So how? So Chanda, from your perspective, how does this go? How the energy exchange system goes for this deep life? Obviously, they are in the fluid, and they are interacting with the environment, which are different minerals. And within this fluid, there are the microbes.
Yes, as far as I know, the chemical reaction will produce energy, and microbial life could could take part in this chemical reaction and get energy from this reaction. Actually, that is important part for microbial life to get energy in the deep surface. But actually, if you ask me what kind of minerals could be reactive, or the bacteria could take part in what kind of chemical reaction, actually I don't know what kind of, because I do not see much details of this kind of paper.
So there are a group of people, mainly from University of Johns Hopkins, and including our collaborator Fang Huang, whose PhD work involves the equation of state of water under high pressure, high temperature conditions. And for their equation, they do consider different cut and onion reactions. including the metallic ones like magnesium, iron for mineral and fluid exchange, but they also consider different types of organic compounds. So I'm just making up those organic compounds, CH3COH or something like that. So they are writing a lot of equations like that and trying to solve them. And you could look at their and basically they're just describing the fluid mineral reaction. But actually, I'm curious about how this energy is being transferred, because it is okay that through this reaction, mineral rock reaction, as long as there's some carbon in the system, I think that they are going to form different kinds of organic compounds, and those compounds could be useful for the microbes.
Yeah.
I think here they're drawing something that's very interesting, but whether I don't know whether that's true or not. So, for example, for figure E, they are drawing here. So, in the present, at the surface, we have the inflow of oxygen. So, and then deeper, they say anaerobic, basically means oxygen poor. And the deeper part, they do have the CO2, CH4, H2 species in the fluid. I assume that's what they mean. Actually, in the fluid, it's not always the case. It's not always charge neutral. They do have charges from different species. I mean, those are organic compounds and in equilibrium. So they're actually in E, it's interesting that trying to form this kind of, let's say, redox front where you form some new minerals. I think, I don't know. It's FeOH. To me, that looks something that it get rid of one oxygen or something. Then you could form a, let's say, anion in the fluid, and might could further react. I don't know whether this is true or not. I mean, they draw something that's interesting. I don't know whether it's really widespread in the deep life. I myself, that not an expert on this, but I'm very curious about it. But still, that didn't help me to understand that how energy is created to support the early life, because life needs energy to survive and as well as to duplicate. I mean, for these microbes, that's how they evolve. And it's also, in my interpretation, that it is during this fluid microbes as well as fluid mineral reaction. That's how carbon isotopes is fractionated, because you have this organic compounds, you have this microbe, which is basically another organic compounds. I mean, it's life, but it is organic compounds like you and me, everyone here in this room, or anyone that is watching this video, you are organic, combination of organic compounds that also trying to bond certain carbon, hydrogen, oxygen, or prefer certain one of the isotopes in certain situations, including sulfur and nitrogen too. And then for this organic compounds, then you can fractionate with other compounds in the fluid, and the fluid could react with the mineral, which further, which have different bonding of carbon, oxygen, sulfur, hydrogen too. And it's this process that basically is at least 3 atom members that fractionate the different isotopes, which needs energy to support lives and like the life to go on, to prosper, to duplicate. And it is also this process that energy, I don't know, because for heat itself, that it probably is okay. So we have this geothermal, that the Earth constantly losing heat from the interior to the surface. I mean, this is pretty close to surface. But heat itself is not enough to sustain energy. I think there's other organic reaction that goes on. I hope that there are some biologists that could help us to understand this process, or someone in microbiology.
Hi, Junao. By the way, how what's the depth they used to define this deep life, like 2,000 or 3,000? Okay, one to four.
1 to 4, yes.
Okay, got it.
But as the Professor John said, that the microbial life could be survived in more depths than the 4 kilometers, but also but this paper just did not mention that. Yes.
So what are the mineral assemblages? Mineral assemblages at, for example, 5 kilometer deep to maybe 8 kilometer, 10 kilometer depth. Turn out. I think that's still it's sort of the upper crust and the middle crust. It's definitely not the lower crust yet.
Just the upper crust, upper continental crust. And most of them may be granites or some intermediate rocks. Maybe some, I think most of the felsic and intermediate rocks for the upcontinental crust is, I think.
Okay. Yeah. If for any of the major accessory minerals in granite that they could infer fairly low temperature, then it's interesting to compile all this data globally and then trying to constrain the temperature, relatively low temperature profile, I mean depth profile as well as temporal. That might potentially provide another constraint to the exactly same question that this paper is trying to presenting. I mean, I myself don't believe 120 degrees is lived life, but it could be a function of the temperature. So at least could make the story self-consistent. Okay, but for this work, let me see. So basically they are showing here for different parts of the cratons, right? So for some part, I mean, those one with a relatively gravenel that's very hot and then they're relatively cold. Then some other parts that looks really cold. I mean, at 1,500 million years, those parts. So where are they? So those ones are, they are like superior 70 degrees, right? Okay.
Yeah.
Actually, this looks like some region that's pretty close to where Jingao Liu published his Nature paper. I don't know if I don't think it's exactly the same location, but looks like very somewhere close.
Yeah, maybe.
Another location. So basically, through his dating, he does get some samples that has pretty high temperature. I mean, all the way to 500 degrees C, or even 600 degrees C. I think at least those temperatures are quite feasible.
Yeah.
Okay. I'm not a low temperature expert, but I do think that's possible to do, as well as possible data that we could obtain in the cyber infrastructure that is available so far, or with a certain amount of data cleaning. Actually, I don't think that is too much effort in collecting data. I mean, should be abundant data for that, because that's pretty shallow, and a lot of publications should be already available and being put into the GeoRock or Earth chemistry. Okay. Okay.
Okay, so do we have any other questions? So any other questions? Oh.
So do you think this is related to the geothermal different accretons, like what they're showing here in terms of the temperature evolution curve, sort of biosignature environment, geochronology formation events? Well, yeah, okay.
And if the paper, they also try to compare the thermal evolution with the biosignatures, but also it should be the geochronological information, because time is important, because if you do not time, you do not know what time the biosignatures exist. So so they also just emphasize that it should have the biosignatures and geochronological information of the events. But actually, I do not know the activity of the biosignatures is actually just to correlate well with the geochronological information of the events. Yeah, because it also just cite other researchers' work. The data is not produced by himself, I think.
Oh, okay. I don't think that's a fair statement. I mean, if they claim, for example, 200 degrees, like say 120 degrees live limit, where in this figure D that you are showing in this slide, then for example, 1400 million years in terms of age, that's much higher temperature than that. So I don't think that they are trying to infer here of any of the real life signature. I think they only mean the temperature, they inferred from the veins.
Yeah.
That's my interpretation. And also the veins might be or might not be related to real life, but they do see the stable isotopic extreme values, some of them with the very extreme values there. Am I right?
Yes, almost right.
So for this 3C, 3D, and 3E, they show something with extreme isotope fractionations, and the 3A and 3B they didn't show.
Yes, but actually, but intriguingly, for this 3B, that is habitable for deep life, but there's no biosignatures, probably because it has to not be reported, or this temperature may not be right. I don't know.
Okay, that's bad. They only have 5 points, and you have one of the prediction that is explainable. Okay, that's fine. That is interesting paper. I think that they do provide some insights for other people to do some further work in different fields.
Yeah, it could guide some scientists to find the microbial life in deep Earth, I think, if it according to this paper, I think.
Okay, I think that's pretty good discussion. I think that's so much for today. Have a good evening, everyone. Bye-bye.